Hi, let us try to integrate the sine of the square root of x. Now I assume that this would work with a substitution. Probably u is equal to the square root of x. But personally, first I always try something else. And in particular, I think I found an interesting technique here, which I will show to you now. But let us just talk about the sine of the square root of x first. It looks quite different than your normal sine of x. Because these waves here keep getting wider and wider, which makes sense because the square root of x is growing more slowly and slowly. The normal sine of x has had its first root at x is equal pi, and then the second root at x is equal 2 pi, which is just twice the first root, right? But here, the sine of the square root of x has its first root at pi squared, which is almost 10, and then it has its next root at 4 pi squared, which is almost 40, which is already 4 times as big as the first positive root. And yeah, so because the square root is just growing more slowly and slowly, that's because this is the reason for those roots spreading out further and further, and that's why those waves here are getting wider and wider. So that is just the function that we're trying to integrate. So now let's talk about how we're going to integrate. And I thought, let's just try a few things out. We basically have a composition of functions here, the sine of the square root of x, and I thought, how about we just try to integrate the outer function first. Of course, this almost never works because you will have to take the derivative of the chain rule, but let's just try and see what happens anyway. So, as I've said, we have the composition of the functions sine of x and square root of x, and we will integrate the outer function first, which would give us a minus cosine. The integral of the sine is the minus cosine, and we will leave the square root of x inside. So we will try the minus cosine of the square root of x, and we will take the derivative of it. I just use a prime symbol for the derivative, f prime, and f in our case is minus cosine square root of x. If we take the derivative of this, then we take the derivative of the outer function, and we leave the inner argument, which is the sine of square root of x, which is exactly what we want, but we have to multiply by the derivative of the inner function because of the chain rule, which is 1 divided by 2 times square root of x. That's the derivative of the square root of x. So that's kind of bad. And the next thing we think about is, can we get rid of this factor, of this 1 divided by 2 times square root of x? And the first guess would be, well, what if we simply multiply this function here by 2 square root of x? Of course, this strategy would normally never work, because then you have to take the derivative of the resulting function, 2 square root of x times minus cosine of square root of x, with the product rule. And if you take the derivative with the product rule, then you add a new summand, which usually is quite a problem, which you can't just easily remove. But let's just try it anyway. So, as I've said, we try to cancel the factor of 1 divided by 2 square root of x, this one here, by multiplying with 2 square root of x. So now, instead of minus cosine square root of x, we try minus 2 square root of x times cosine of square root of x, and we take the derivative of this. So at first, what we get is this function, minus 2 square root of x, times the derivative of this function, which is the derivative of cosine of square root of x, and that would be minus 2 square root of x times the derivative of cosine of square root of x, which is just minus sine of square root of x divided by 2 square root of x, and that multiplied by minus 2 square root of x, that just leaves us with sine of square root of x, which is exactly what we want. But as I've already said, product rule. We now have to do it the other way around too. We take this factor, 2 square root of x, and have to multiply it with now we have to take the cosine of the square root of x and multiply it with the derivative of this factor, with the derivative of minus 2 square root of x, and add it to sine of square root of x. So what do we get? if you take the derivative of minus 2 square root of x, then you just get minus 1 divided by square root of x. And that times the cosine of square root of x. So you get this additional summand minus cosine square root of x divided by x. So we could try and remove this minus cosine of square root of x divided by square root of x by adding a function here which has plus cosine of square root of x divided by square root of x as derivative. But that's honestly really easy to do. I mean, you basically have the composition of two functions, cosine of x and square root of x, and then you multiply it by the derivative of the inner function, which is this 1 divided by square root of x here. And to remove and this is really easy to integrate, all you have to do is integrate the outer function, which is the minus cosine of x, and which, if you integrate it, gives you minus sine. That's very easy to do. Let us write this down. We see that for this factor, if we divide it by 2, we see minus cosine of square root of x divided by 2 square root of x is really just the minus cosine of square root of x times 1 over 2 square root of x, which is just the derivative of square root of x. So really, this problematic term here, this minus cosine of square root of x divided by square root of x, is really just minus cosine of square root of x times square root of x prime, or basically the composition of two functions times the derivative of the inner function. And as I've already said, this is really easy to integrate. All we have to do is we have to integrate the outer function, the minus cosine. Again, here for a recap, this is like taking the derivative of the composition of the function's cosine of square root of x multiplied by the derivative of the inner function, square root of x. Because of this, we see that 2 times the sine of the square root of x prime is just cosine of square root of x divided by x. Or the integral of cosine of square root of x divided by square root of x dx is just 2 sine of square root of x. You know, all you have to do is integrate the outer function. The integral of the cosine is the sine. So, with that being said, in total, we now get that if we add this 2 sine of square root of x to this test function that we had here, then we get the desired result, right? If we take the derivative of minus 2 square root of x times cosine of square root of x plus 2 sine of square root of x, then what do we get? Again, at first we have this factor times the derivative of this factor, which is just minus 2 square root of x times minus sine of square root of x divided by 2 square root of x, which is really just the sine of square root of x. That's what we want. But then we get the problematic term, which is the derivative of the square root term times this. And the derivative of minus 2 square root of x is really just minus 1 divided by square root of x. And then you multiply it by cosine of square root of x. So we get this problematic term of minus cosine of square root of x divided by square root of x. But with this 2 sine square root of x, we remove the problematic term, right? Because the derivative of 2 sine square root of x is just 2 cosine square root of x times the derivative of square root of x, which is times 1 divided by 2 square root of x. And that will give us cosine of square root of x divided by square root of x, which will cancel with this minus cosine of square root of x divided by square root of x. And so we get the sine of square root of x. Right? And so we are done. We successfully integrated the sine of the square root of x. The integral of the sine of the square root of x dx is just this thing right here. Minus 2 square root of x times cosine square root of x plus 2 sine square root of x. Let's just quickly verify it by a program too. I mean, I did verify it here. I took the derivative of this. But this is the graph for this integral here. This is the graph of minus 2 square root of x cosine square root of x plus 2 sine square root of x. It already looks like it makes sense. This function is growing very fast. Because of this plus 2 sine of square root of x term here. But it seems like it makes sense. There could be an extreme value here, right where the root is, which is close to 10, which is exactly as it has to be. I mean, this red function, which is sine of square root of x, has to be the derivative of this green function, so it has to have its root where the green function has its extreme value, which seems to be true. And again here around the 40, that's where the minimum point here could be. So it already does look like it makes sense. And now we will just let this program verify it. Let's add the derivative function. The language here is German, but you already see the dy over dx symbol here. So this is really just add the derivative. And if this is the correct derivative, then this purple graph will overlap with the red graph, which it indeed does. The derivative of this green thing is indeed sine of square root of x, right? So now that we clarified this, let us keep on talking, because you probably realized that my idea would work as soon as we were here, because you probably immediately saw that this cosine of square root of x divided by square root of x term is really easy to eradicate, because this is, as I've said, just this composition of functions, and you immediately see that it's multiplied by the derivative of the inner function, which is 1 over 2 square root of x. And what you also should notice, and what I of course immediately asked myself is, wait a minute, shouldn't this strategy always work if I want to integrate if I want to integrate functions of the form f of square root of x? Shouldn't it always be possible to integrate these type of functions in this way? And all we really had to do is we integrated the sine, which became a minus cosine, and which is here minus cosine. We put a 2 square root of x in front of it, and then we integrated the integral basically. The integral of the sine was the minus cosine, and then we had to integrate the minus cosine, which became a minus sine. And then we had to subtract the minus sign, which is adding sine. So shouldn't you be able to integrate functions of the type f of square root of x as long as you can just integrate the outer function f twice? I will show you what I mean here. If you in general want to integrate functions of the form f of square root of x, then you should be able to do it as follows. We notice that this strategy should work in general. Let f from R to R be a function, capital F from R to R be an antiderivative of small f, which just means that the derivative of big F is small f. I really don't like the term antiderivative, by the way. This word doesn't even exist in my language. I think that this is just a very weird thing. And then we need to integrate the integral of f, right? We basically need to integrate f twice. So now we need an antiderivative for capital F. So let capital G from R to R be an antiderivative of capital F. Then what I say is that the integral of f of square root of x dx is just 2 square root of x times capital F of square root of x minus 2 capital G of square root of x. And in fact, in our case, the small f, the function f that we wanted to integrate was just the sine of x, right? Sine of square root of x. And then the capital F, the first integral of the sine of x, was just minus cosine. And it's indeed right. 2 capital F is then just minus 2 cosine square root of x, and then times 2 square root of x, like here. And then minus 2 capital G of square root of x. And capital G was just, you know, integrating small f twice, or integrating sine twice. After the first integral we get minus cosine, and then after the next integral we get minus sine. And this does work. We have here minus 2 times minus sine, which is just plus 2 sine of square root of x. So this formula did work in our case. And in fact, this formula does always work. And in my next video, I will talk about this formula. So see you guys then.